First of all, thank you to the organizer for giving me the opportunity to talk here. So I thought of starting with a little two words. Like Rohini was so I did my integrated PhD over here, and Rohini taught us standard model. And when I joined here in the physics department, then I moved to the Center for High Energy Physics as a graduate student. And I remember Rohini in our standard model course, she used to travel a lot during the weekdays, and many of our classes are over the weekends. And she used to say travel maybe if, Sunday very late, Friday very late night, and then Saturday very early morning she comes in for class. And I really, at that time, that moved me a lot. Like the amount of energy she had at that age itself was something I really appreciate at that, and we really enjoyed. I mean, she was a passionate teacher. I think what Anuradha also said. I mean, she was a passionate teacher, and that I always keep. That is always in my mind. Later, we also collaborated. So during my very last year of PhD, I collaborated on a SUSI project where Kirtiman Sudhir was also there. This is on something called charge and color breaking minima in SUSI theories. At that time, this MSSM we were looking at, and we actually gave some. After the Higgs discovery, we saw that what will happen if the Higgs Zeno parameter actually goes very large, and that would actually make the electric vacua metastable and soon after unstable. So that paper was actually, I don't think it went to any of our thesis, not me, not Kirtiman's, but that paper was very well received in the community. And I think we have talked various places, both me, Rohini, Kirtiman, maybe Sudhir also, that thing. So today what I wanted to discuss is some work which we did recently about on multipolar dark matter. So the question is, like, I don't need to really give an introduction why we talk about dark matter. So despite evidences at various length scales, we still know very little amount in information about the dark matter. Now the point is, what we know probably is that the amount of the charge a dark matter can carry is fractionally very small, it's tightly constrained. But it nonetheless stops us to think about what would happen if a dark matter is a fermion and it has a higher moment coupling, like multipolar, like monopole or dipole terms. For example, this is the magnetic dipole moment. So if the chi is a dark matter and if nu is the photon, then this is the magnetic term and this is the electric dipole moment. Now, the kind of thing, this kind of dipolar interaction of a dark matter and the photon, what it gives that it has a derivative coupling, and derivative coming from the derivative in the F mu nu, the field strength tensor, and that has a quite rich phenomenology, and which we'll see more. So later, so this was known, but then around 1957 or around that period, Zeldovich actually proposed that not only these are the two couplings one can actually write for a fermionic dark matter, but also one can write something similar to a called anapole moment, which looks like this. Now, what is the anapole? So anapole, it doesn't have a typical classical electrodynamics analog of a multipole moment, like multipole, like dipole, quadrupole. It doesn't have. So what happens, you can think of like an analogy as an analogy. So if the current is flowing in this direction, the magnetic dipole moment is on the upper, like going up. But what you can think of that the anapole moment is like if within the toroid the current flows, the current direction is along that, and then the moment what we'll have, or the toroidal dipole moment, that would be something related to what we call anapole. Or if you write, so as you know that if you write the interaction energy of a magnetic dipole or a magnetic electric dipole, that will be like sigma, like the spin just directly couples to the magnetic field or the electric field. Whereas for anapole, it actually directly couples to the current. Or in the Lagrangian level, the terms look like this. But so what you can see that a Dirac fermion can have magnetic, electric as well as a anapole moment, but for a Majorana fermion, the only first non-zero part which you can have is the anapole one. You can just check by just this term, if it's a Majorana fermion, it will be 0. So this was already known 1957-ish or onwards. So what we actually try to look that if you have this kind of coupling, if you have like say dipole or a magnetic dipole or electric dipole or anapole moment, what will happen to the dark matter phenomenology? Okay. So now, for example, the very first thing is that the relic density. The relic density here we are basically considering the WIMP-like situation where at the early universe there is an equilibrium between the annihilation rates between the standard model and the dark matter sector. Then as universe cools down, then the dark matter freezes out, and the number density is governed by the Boltzmann equation. Now in this case, as you can see that given this interaction for the anapole case, we have these two vertices where like this is the anapole vertex and this is the standard fermion, this is the electroweak vertex, electromagnetic vertex. Whereas this vertex is also there, but at the tree level one can actually check that this vertex or this diagram, the T-channel diagram, actually doesn't contribute. This is on-shell for on-shell photons, one can check that. So main contribution for all this relic density for anapole system is basically via this channel. So this is what sets the relic density. Then what comes is that detection. So how do you detect those things? So usually the direct detection follows like the dark matter particle scatters off a nuclei and the recoil rates are measured with the detectors. The recoil rate, differential recoil rate are proportional to the exposure time, inversely proportional to the nucleus, target nucleus mass, the dark matter local dark matter density, the dark matter mass, and this extra factor which are nothing but the differential scattering cross section and the velocity distribution profile. And in this case the upper limit is basically the escape velocity in that case. Okay. So now, so this is the standard dark matter detection where your Lagrangian input goes over there. Now the point is that when you have this kind of momentum dependent coupling, it actually facilitates the dark matter capture. How? So you see that a dark matter in a celestial body can attract a dark matter in its gravitational field and it will just pull it. So once dark matter pulls it, the velocity increases. As a result, the dark matter, when the dark matter scatters with the celestial body or the standard model particles which are inside the celestial body, it loses energy, and as a result, that the energy which after it loses, the dark matter gets finally captured. So now this final dark matter got captured, so they will accumulate, and this accumulated dark matter inside the celestial body would annihilate, and that increases the surface brightness of the stellar systems. And those things, one that from the Earth-based observatories or space-based, they can actually see some signals for that. So like surface brightness increasing. Okay. So now what happens for the anapole? Why we talk about? So as we see that we already had momentum dependent interaction. So as a result, that in the case of an advantages for anapole is the momentum dependent interaction, which makes the dm velocity is very close to the escape velocity of the for the case of the celestial body, and this actually boosts the scattering cross section. So scattering cross section of the dark matter and the standard model, the scattering cross section via which this dark matter gets captured. So now what happens, the neutron star being an extremely dense object, the escape velocity is around 0.6 times the velocity of light. So now once dm annihilates this, as I said, that it loses energy, annihilation product gets trapped and it actually later heats, because that adds to the stellar heating. Now this temperature or the surface brightness, you can convert that, is either proportional to how much fraction has been captured, or as well as the dark matter density in the neighborhood of the celestial body. And this F is also dependent, the fraction of the capture depends on the scattering cross section. So that means if you have a larger cross section, the fraction increases, surface brightness increases. So that's the basic idea. And so in this case, as you see, the neutron star being many rich in the neutron, but the neutron do not couple at doesn't have an electromagnetic type of interaction, but the next order, which is like an EDM type of interaction or sigma mu nu type of interaction, so that with the neutron, which is suppressed by, which is basically at the loop level, which is suppressed by the nucleon mass, whereas with the proton, it has a tree level coupling, the proton being charged. But what we saw what we assume that as you see the neutron star, if you check the capture rate, the proton density, number density is much smaller, and you had taken say roughly 1% of that, and the neutron, which is their ambient ample amount in the neutron star, so they have a loop level. So now you see that the neutron, by the number density, they are like actually matched up with the tree level coupling with the proton, and we saw that more or less the contributions are smaller, of the same order. So now with this kind of thing, that old neutron star can cool down to around 2000 Kelvin or so, and this kind of temperature are actually can be explored by the infrared telescopes like the James Webb. So this is the main capture, and as I was telling, that if you see that the capture cross section or the scattering cross section, when it is normalized to some non-momentum dependent cross section, that goes very fast for an anapole, as well as they also go, but they are not that steep compared to the anapole for the magnetic dipole and electric dipole. As you see, we are here around 0.6 times the escape velocity, and you see that it can go as large as 10 to the power like 10 order, more than that. So the more massive it is, or more neutron star has a larger escape velocity, so that has a larger boost. So that means larger cross section, larger capture, as a result the surface brightness. So now what the other part? So other way, the neutrinos also can be, so the dark matter can also be captured in the sun, but in the sun this annihilated product of the dark matter which are captured in the sun, they can escape the annihilated products from the sun from the solar interiors, for example neutrinos, and these should produce a neutrino signals at say experiments like IceCube or Fermilab or AMS. So the number of dark matter particles in the sun is basically is a combination of the capture and annihilation term and the evaporation term. Okay. So now for the most of the cases, what happens in the mass range which we are interested in, the evaporation term which are neglected. But looking at the capture rate, so capture rate is a function of the density and as well as the velocity of the dark matter particle at a distance r. So if you think of an inner, these neutrinos are coming from the inner side of the sun, so at a distance r, it has a velocity omega of r, w of r, as well as there is a velocity distribution of dark matter in the rest frame of the sun, this is the u of x, and the capture probability, what is the probability of capturing the dark matter with the velocity omega r that interacts with the nucleus. So with that capture rate, and in the annihilation, the capture rate and in the equilibrium, the capture rate and annihilation rate do have a relation, and neglecting the evaporating term, so what can write the differential flux of neutrino flux reaching the earth are of course inversely proportional to the distance, directly proportional to the annihilation rate, and it is also proportional to the neutrino spectra of DM annihilations. Okay, so with all these ingredients, so basically I have neutrinos coming from sun, this is a part of the capture, earlier one as a capture of dark matter in the neutron star, and the direct detection. These are the main three major contributions for the in these kind of models. So what we saw that, for example, on the black line, the dark matter is actually satisfying the Planck-Rayleigh bound. On the the hatched region are ruled out due to the fact that the mass of the dark matter is larger than the scale of the EFT as a scale of lambda. The blue shaded region are ruled out from the direct detection either from the dark side or from the Lux Zeppelin, whereas the green shaded areas are mainly from the bounds coming from the neutrinos emitted from the sun using deep core IceCube, okay, and also the latest deep core result. So given the shaded area and the hashed area, we saw that only two small regions are still surviving for the case of anapole. Okay, so now you see that this is fine, but then this region which is actually left, luckily also comes under the purview of a neutron star in our neighborhood from the James Webb telescope. And so if it is surface brightness around 2000 Kelvin, so that space, this white space will also be provided this is in the JWST range. So what we see that already the region are actually highly constrained, and in the future the JWST will be completely able to probe or sort of rule out the allowed regions in the parameter space. okay, of this kind of case, anapole. Now the situation is even bleak for the case of the magnetic or electric type of dark matter cases, where already the direct detection rules out most of the parameter space, if not the EFT validity in this case. Okay, so most of the case, so think of in this case almost there is no parameter space left, whereas if you do not consider the EFT validity, there was a small space which is dark matter is still satisfied, but then it goes out. But still, for the reference, for the sake of reference, this is the projected limit from the neutron star heating using JWST. Okay, so as a result, the maximum parameter space is ruled out from the direct detection, and at low mass region, the neutron star actually puts better constraint. So that kind of ends to the talk is that the derivative coupling, as this kind of multipolar dark matter has, where they are actually, by enhancing the scattering rate, they increases the dark matter capture in the celestial body, and they probe that now for this kind of interaction, the celestial body actually plays an important role for detection rather than an Earth-based system. Whereas the updated detection bound and the capture disfavor the viable parameter space in the EDM and MDM case. A nano parameter space for the anapole is still surviving, and which are in the range of the JWST. So what happens that in the lower mass regime also, if you go even lower, so there the JWST in this case would be actually playing an important role. Thank you.